in a long series of videos on polynomials and series. So let's just warm up here and answer some of these questions so that we're familiar with the notation. So first, given that p of x is equal to x minus a, k is an integer, a is constant, find p prime, p double prime, this is p triple prime, this is the fourth derivative, and this is the nth derivative. Okay. Well, this shouldn't be too hard to do. So p prime, then, applying the power rule, should just be k times x minus a times the derivative of the inside function, which is just 1. Oh, and I forgot, this should have been k minus 1. Okay. Then p double prime, the second derivative, is the derivative of the first derivative. So this is k minus 1 times k times x minus a, k raised to the k minus 2. P triple prime, or I'm just going to put the 3 there using that notation, is k minus 2 times k minus 1 times k x minus a raised to the k minus 3. And if we were to continue this process, well, let's go one more, I guess, before we continue the process. This would be k minus 3 times k minus 2 times k minus 1 times k times x minus a, k minus 4. So if we were to find the nth derivative, well, what we're doing is essentially this process, but n times, and this would seem like this should remind you of the factorial. So this would be k minus, or k times k minus 1 times k minus 2 dot dot dot. We're going to do this n times. And then that whole thing times x minus a raised to the k minus n. Okay. So this is this process here is factorial like, or similar to the factorial process. Okay, and this is somewhat important. We're going to return to this a little bit later on. But that concludes the warm-up. Now let's talk about the goal here of what we're trying to accomplish, because Taylor polynomials are kind of a rich topic, and there's a lot you can do with these. You can just throw a formula on the screen and then manipulate the formula, or we can also get into some very rigorous proof. But I'm going to approach this lesson in this way. I'm going to start with a specific problem, then I'm going to solve it, and then I'm going to expand the solution to other problems. Okay. Then I am going to get a general solution, and then we are going to look at some theoretical and practical implications. Okay. So I'm going to take you through this process, perhaps similar to how Mr. Taylor figured out these polynomials, starting with a specific problem, solving it, expanding it to the solution to some other problems, finding a general solution, and then considering the theoretical and practical implications of this. So let's proceed onwards. And first, we have our specific problem. Estimate the value of sine of 2 pi over 13 as accurately as possible. And when we're looking for, we want to use a method that can be extended for other values and other functions as well. So, and I know some of you are thinking, well, why don't we just plug this into a calculator? But the goal here is to understand how calculators work. So here's the sine function. And 2 pi over 13 is somewhere over here. and we want to know what is that value. Okay? We really want to know what is that value, and we want like an exact value as accurately as possible. So exact would be perfect. The next best thing is to do this as accurately as we possibly can. So we're going to use a method that we know already, which is the linear approximation. Okay. And I'm going to zoom in on this picture a little bit. Okay. And let's just kind of recap what linear approximation is. We select a special point. And special point here is my particular notes. I'm sure other people don't refer to it that way, but I think of this as a special point, such that we know the exact value. And then we're going to use this point to find a derivative and to find the equation of a line. Okay. So let's say I zoom in really big on this. Okay. So 2 pi over 13 is very close to pi over 6. So our special point here we're going to use is x equals pi over 6. So this is pi here. So pi over 6 is around, I'm sorry, this is pi over 2. So pi over 6 is like right here. And then 2 pi over 13 is a little bit to the left of that. So this is 2 pi over 13. Okay. And what we're going to do is find the tangent line through that point and then use the tangent line to help us estimate what is the value of sine of 2 pi over 13. Okay. So I'm sure all of you are capable of doing this at this stage in the calculus curriculum. So I'm going to hit pause, solve it, and during this time, and you should do the same thing. Okay, so there it is. You have your solution. So I did the original function is sine. Take the derivative of that, it gets me cosine. Substitute in pi over 6, it gives me the slope of the line using point slope form. Pi over 6 for x1, sine of pi over 6 for y1, and making the substitution, and this is the equation that I get. And now, if I wanted to make the estimate for 2 pi over 13, then I can substitute in y of 2 pi over 13, and that's equal to root 3 over 2 times pi over 13 minus pi over, 2 pi over 13 minus pi over 6 plus 1/2. That's equal to, that gives me a value of 0.465, which is really close to the actual value. Okay. So here we have a specific problem of estimating the value of sine. Okay. And we want an approximation that's as accurate as possible. And this is essentially review. All we've really done is talk about linear approximation, which we already know how to do. Okay. So I'm going to end this video right here, and then in the next one I will talk about, we'll investigate the pros and cons of this method. Thank you for watching. Have a wonderful day.